Today we're going to revisit the concept of center of mass, which we've touched on a couple of times, and even after today we'll touch on again later in the class. As a reminder, for any system there's a point called the center of mass, which is sort of like the average position of the masses. We define it according to the following definition. If we have a number of point masses, m1, m2, etc., each located at positions x1, x2, etc., then we define the center of mass as the center of mass position is the sum of the following: m1 x1 plus m2 x2 plus m3 x3 and so on over the sum of all the masses, m1 plus m2 plus m3 and so on. Textbooks like to write it this way. I am a big fan of a slightly different format, which you'll see in the bottom down here, which is that the mass of the system times its center of mass position is just the sum of each mass times its position. So we just keep adding these things up. I'm a fan of that in part because it means that there's complete symmetry in how we define these things, in which everything in the system has something, which is m times x, and the system itself has something, which is the system mass times its center of mass position. Notice that the system mass here is the same as this. So all I've done is algebraically solve it over, and it's not any different in a mathematical sense. All right, let's take this out for a spin. If a 5 kilogram object is at x equals 0 and another is at x equals 6, where is their center of mass in meters? So we have our 5 kilogram object here and another 5 kilogram object, and we're told that this is x equals, this is x equals 0 and this is x equals 6. So m1 is 5 kilograms and m2 is 5 kilograms. Then the center of mass position is 5 kilograms times 0 meters plus 5 kilograms times 6 meters, all over 5 kilograms plus 5 kilograms, which is 30 kilogram meters over 10 kilograms, or 3 meters. And maybe not surprisingly, the center of mass, which is usually made with a little cross like that, is exactly halfway between them. And we'll keep coming back to this. There's a symmetry in this situation. It can't be closer to one or the other because we can't tell which is one end and which is the other. All right, a 5 kilogram object is x equals 0, and a 10 kilogram mass is at x equals 6. And we want to find where is their center of mass. Here I'll draw this bigger to say that it's more massive, but remember these are really being treated as point particles. So again, we can say the center of mass position is 5 kilograms times 0 meters plus 10 kilograms times 6 meters over 5 kilograms plus 10 kilograms. So this ends up being 60 kilogram meters over 15 kilograms, which is 4 meters. So the center of mass is something like, if that's the midpoint, it's something like here, closer to the heavier object, which is a general thing we'll want to keep in mind. The center of mass is, in some sense, drawn to or heavily influenced by the more massive objects and less by the others. Right. Notice also, and it's not at all a coincidence, that the ratio of distances, right, if that's 4, then clearly this is 2. And notice that for a 2-mass system, the ratio of distances for the center of mass is going to be inverse to the ratio of masses. In other words, the heavier mass is twice as heavy, but only half as far. And this will come up again when we do rotations. This will be a useful way to remember things. All right, how about a 10 kilogram object at the origin and a 5 kilogram object 6 meters away? And your first instinct might be, well, it will be the same place. And that's not true, but also not false. In other words, you have to be careful what you mean when you say that. Right? We would say that now XCM is 10 kilograms times 0 meters plus 5 kilograms times 6 meters, all over 10 kilograms plus 5 kilograms, which is 30 kilogram meters over 15 kilograms, or 2 meters. So the center of mass is at 2. And you can see that that is clearly really the same situation. We've reversed our axes, and so but we still have a 2 to 4 ratio. And again, the distances are inversely to the masses. Pointing out that it doesn't really matter. The center of mass location in your coordinate system will depend on where your origin in your coordinate system is, but its arrangement relative to the other parts of the system will end up always being the same. All right, that's easy for point masses, but it gets more complicated for extended objects where you can't say this thing is at one point, but rather occupies a bunch of places. For instance, objects with high symmetry, though, will have the center of mass at the point of symmetry. So, for instance, if we have a balanced meter stick, which is, of course, 1 meter long, and since its balance is uniform in density, then its center of mass would be at the 50 centimeter mark. If we have a sphere, a uniform sphere, the center of mass would be at its center. But be careful, there doesn't have to be any mass actually at the center of mass. For instance, the center of mass of a donut, right, if we think of not the world's best picture of a donut, that was pretty bad. The center of mass of the donut is at the center of that torus, even though there's no matter there, even though that's empty space. So be careful, because the center of mass describes where the average mass would be, but there might not be a mass at that point. In more advanced classes, we'd spend a lot of time figuring out how to get the center of mass for unusually shaped objects. That's a thing covered, for instance, in AP Physics C, but it is not something which is covered at this point. All right, we're going to walk through an exercise with these following two objects that we've had. We have a 2 kilogram object starting at x equals 0, and a 4 kilogram object starting at x equals 12. And they're going to have some velocities, 2 meters and 1 meter per second. And at first I want to find their initial center of mass, which will be easy. This is actually going to look, well, we'll do it. 2 kilograms times 0 meters plus 4 kilograms times 12 meters, all over 2 kilograms plus 4 kilograms, which is 48 kilogram meters over 6 kilograms, or 8, a position of 8. So the center of mass is, let's do that maybe in red. If that's halfway between them, then the center of mass is at 8. And by the way, as an aside, notice how we have 8 to 4. This looks a lot like our 5 and 10 kilogram masses, just from the accident of having a 2 to 1 mass ratio. Anyway, nothing very deep about that. Same setup. Now we want to figure out where the center of mass is at 3 seconds. So we need to figure out their positions. So let's say this guy, the 2 kilogram object, is going to start at 0, and he gains 2 meters per second for 3 seconds. So it's at 6 meters. And the 4 kilogram object starts at 12 and loses 1 meter per second for 3 seconds, so ends at 9. Then the center of mass is 2 kilograms times 6 meters plus 4 kilograms times 9 meters, all over 2 kilograms plus 4 kilograms, or 12 kilogram meters plus 36 kilogram meters, all over 6 kilograms. But this is, again, 48 kilogram meters over 6 kilograms. So we get the kind of interesting thing that 3 seconds later, it's still, the center of mass is still at 8 meters. Okay, same setup. We want to know when they collide. That's going to be relatively easy. We're going to take the position of the 2 kilogram object and set it equal to the position of the 4 kilogram object. So 0 plus 2 meters per second times the time of collision is 12 minus 1 meter per second times the time of collision. 3 meters per second times the time of collision is 12 meters. The time of collision is 4 seconds. So it hits just a little bit later. All right, if these two things have collided inelastically, what is their speed after the collision? Drawing our picture, we have this thing running into this thing, kablooey, and then we get some combined thing moving off. And that's what we want to find. So remember, this was moving. This is 2 kilograms moving at 2 meters per second. And this one is 4 kilograms moving at 1 the other way. And so we end up after, and we want to know what is this. And of course, we have 6 kilograms combined. But this is just a momentum conservation. So we'll say the initial momentum is the final momentum. So 2 kilograms times 2 meters per second plus 4 kilograms times minus 1 meter per second is 6 kilograms times the final speed. But then something interesting happens, right? We get 4 kilogram meter per second minus 4 kilogram meter per second is 6 kilograms times the final speed. So the final speed is 0. The final speed after their collision was 0. They come to rest, right? So technically, although I'm going to leave this drawn up here, they shouldn't really be moving. All right. What is the center of mass at the moment of collision? Well, again, now we want to say that x2 was 0 plus 2 meters per second times the 4 seconds where the collision was, so 8 meters. And of course, that has to equal x4 because the point of collision is there's the point of collision, so they collide. So their center of mass, they're at the same place. The center of mass would be the mass 2 kilograms times 8 meters plus 4 kilograms times 8 meters all over 2 kilograms plus 4 kilograms. We can see that the 8 meters can be factored out, and we're going to, well, I guess we'll do 16 kilogram meters plus 32 kilogram meters over 6 kilograms, which is, again, 48 kilogram meters over 6 kilograms, or 8 meters. So a couple of interesting things. They collided at the center of mass, and they sort of had to, because if everything's at the same place in the center of mass formula, then the center of mass is also going to be there. So if all of the system is at one point, the center of mass must be at that point as well. They have collided at the center of mass, and they don't move off. Since they don't move off, the center of mass position, again, stays at 8, because nothing's ever going to change from here, telling us that the center of mass starts at 8 meters, and it remains at 8 meters throughout for the whole thing. It's not affected by the collision. It doesn't get moving. It doesn't get stopped. And that's pretty suggestive. All right, so let's see if that holds as a general thing. We have our 2 kilogram object, and we have our 4 kilogram object moving the other way. But this time, we have 2 kilograms moving at 3 meters per second, hitting something which is 4 kilograms moving at 1 the other way. And you should copy and fill in this chart, which is just find the positions of both things and of their center of mass. Let's assume for simplicity that again, they collide inelastically, that they stick together. And so as you fill out these things, at some point they will collide, and then give them a unified velocity and carry them out. What comes out is what's on this chart. And you should confirm it, or confirm a few of them that you believe it, but the 2 kilogram guy goes 0, 3, 6, 9, etc. And the 4 kilogram guy does this. They collide at 3 seconds now. You can see because they have the same velocity. And after that velocity, they stick together and move off at 1/3 of a meter per second. So we get this. But the center of mass is kind of interesting. It changes location over time. Let's see it just up until the collision. It moves over, and it looks like this position is changing by 1/3 of a meter per second, as if it had its own velocity, as if it were a thing that's moving. And of course, the velocity it has turns out to be the same velocity that they have after collision. In other words, the motion of the center of mass wasn't affected. It's always moving off at 1/3. Even though the collision goes on and changes them radically. All right, this is sort of a goofy little cartoon of this rendered in Desmos, where the two objects are shown and then they collide and they move off. They're offset a little bit just so you can track them as they move after the collision. So, all right, and it will repeat. Here we have our 2 kilogram mass coming in and our 4 kilogram mass coming in, and we get that they collide. Oops. Let's watch that again. And the center of mass is marked here, and notice it just drifts over at a constant speed, and it doesn't really matter before or after the collision. It's always at that speed. In fact, consider the definition of the center of mass in this case, and I'm going to use the one I prefer, which is that the sum of the masses times the center of mass position is each mass times its own position added up. We can see that if we then look back a little bit later, we'll get some delta x's in each of those places, and that will give us some change in the center of mass position, potentially. And then if we divide by the time interval it took to make these changes, we would end up getting that the center of mass, the sum of the mass in the system times the velocity of the center of mass is m1v1 plus m2v2, but these are the momenta, right? This is the momentum of object 1, and this is the momentum of object 2. And we're adding them, so this is the system, right? This is P system, the system momentum. And over here, this is, since we have the mass of something times the velocity, we might call that P of the center of mass. Now, whereas the center of mass kind of looks like it has its own momentum, and that momentum is equal to the system momentum.